Dear students, welcome to the Physics Virtual Lab for Grade 11. I'm Anand, Faculty of Physics at the Delhi Public School, Bangalore East. In the sixth experiment of this series, our aim is to determine the coefficient of viscosity of a liquid of high viscosity. This we do by measuring the terminal velocity of a steel sphere descending through it. For this experiment, we need the following apparatus: a long cylindrical jar of diameter 5 cm. This jar is about 150 centimeters long and is usually referred to as a Stokes'Viscometer. A transparent viscous liquid, usually the Stokes-Viscometer, is pre-filled with this liquid. A clamp with a stand and a scale. Steel balls used in ball bearings. We may need a dozen of them. Though we are supposed to collect data only for 3 trials, we need quite a few steel balls for repeating trials that may be unsatisfactory. A screw gauge to measure the diameter of the steel balls. A stop clock to time the descent of the balls between a certain fixed distance. The leftmost image is a full view of the Stokes-Viscometer along with the clamp. The graduated scale is not visible in the full view. Look at the image at the center. This is the graduated scale zoomed in through the viscometer. The third image shows a steel ball held between the stud and the spindle of a screw gauge. This is an image of the stop clock that is provided. Look carefully inside the stop clock. It has two scales to measure the position of the seconds hand. The inner one has the interval of 60 seconds divided into 60 divisions and therefore has a least count of 1 second. The outer one has the interval of 60 seconds divided into 100 divisions and therefore has a least count of 0.6 seconds. Going even by the lowest of the least count, the minimum uncertainty in time measurement is 0.6 seconds. But synchronization errors add to this uncertainty and make it even worse. For a time of descent which is around 3.5 seconds in our case, an uncertainty exceeding 0.6 seconds gives an error in time measurement that exceeds 20%, which is just not acceptable. So we discard this clock and instead use the stop clock application that comes with all modern mobile phones. These clocks have a least count of around 1/100th of a second, which is fantastic. Now let's look briefly at the theory behind this experiment. When a body is dropped in a viscous fluid, three forces act on it: the gravitational force, which acts downward, the buoyant force, which acts upward, and the viscous drag force, which too also acts upward. Of these, the gravitational force and the buoyant force do not change as the body descends, but the viscous force, which depends on the speed, increases as the body accelerates downward. Initially, the net force is downwards, and therefore the body accelerates downwards. But the net upward force keeps increasing because of the increasing viscous drag force, and at one stage, the net upward force equilibrates with the net downward force. At that point, the ball is said to have attained a state of dynamic equilibrium. Beyond that point, the ball descends with a constant velocity called terminal velocity. Our next goal is to arrive at an expression for the terminal velocity. This we start by writing down the expressions for the three forces. First, the gravitational force. The gravitational force is equal to mass times the gravitational field strength G. Mass is volume times the density, and you know that the volume of a sphere of radius r is 4 by 3 pi r cube. Next, the buoyant force. According to the Archimedes principle, the buoyant force is equal to the weight of the liquid displaced, which is equal to the mass of the liquid displaced times the acceleration due to gravity. Mass of the liquid displaced is volume of the liquid displaced times the density of the liquid. Density of the volume of the liquid displaced is exactly the same as the volume of the ball because the ball is fully immersed in the liquid, which is 4 by 3 pi r cube. And finally, the viscous drag force. The viscous drag force on a sphere of radius r moving through a liquid of coefficient of viscosity eta with a speed v is given by the Stokes expression as 6 pi eta rv. Once the expressions for the forces are in place, next apply the condition for dynamic equilibration. That is, the magnitude of the net upward force is equal to the magnitude of the net downward force, which gives us the boxed expression. There is only one value of speed which satisfies this equation, that is the terminal speed. V with the subscript t represents the terminal speed, which is a solution to this equation. Rearrange the expression and write the equation for the terminal speed. Invert the expression for terminal speed and write down the equation for the coefficient of viscosity. Now take a good look at the equation for the coefficient of viscosity. Here, the density of the steel ball rho, density of the liquid sigma, and gravitational field strength G are all given quantities. The only quantities that are to be measured are number 1, the radius of the ball r, and number 2, terminal velocity v sub t. This equation allows us to calculate the coefficient of viscosity of the liquid by measuring these two quantities. This completes our brief review of the theory behind the experiment. Next comes the actual measurement part. The first quantity we are going to measure is the ball diameter. For this purpose, we use a screw gauge. The screw gauge that we used had a pitch of 1 millimeter and has 100 divisions on the circular scale. So the least count of the screw gauge is 1/100th of a millimeter or 1/1000th of a centimeter. With nothing between them, close the gap between the stud and the spindle of the screw gauge. Once the spindle touches the stud, use the ratchet for tightening. Check if the zero of the circular scale lines up with the baseline. If not, record the zero error. Next, hold the ball gently between the stud and the spindle and tighten using the ratchet. Record the pitch scale reading and the circular scale reading. Estimate the diameter, not forgetting to account for the zero correction. Read the scales and record the diameter yourself, making a table like the one shown here. Because there may be slight variations in the diameters of the balls, measure the diameters for 3 balls and take the average value of the 3 trials as the mean diameter. From the measured diameter, calculate the radius. For the convenience of our audience, a close-up image of the circular scale and pitch scale are shown for zero error configuration and diameter measurement configuration. Pause the video here and record the readings for the zero correction and the first trial. Once you're ready, proceed to the next slide. Pause the video here again and record the readings for the second and the third trials. Once you're ready, proceed to the next slide. The second quantity that we measure is the terminal velocity. This we do by timing the motion of the ball between two markers separated by 50 centimeters. Set the first marker at least at a distance of 30 centimeters below the surface of the liquid. Otherwise, the ball might not have attained dynamic equilibrium and may still be accelerating. The surface of the liquid was at the 115 centimeters mark. So we have set the top marker at the 80 centimeter mark, which is 30 centimeters below the liquid surface. Place the bottom marker at the 30 centimeter mark. Thus, the distance between the markers is now 50 centimeter. Let's now proceed to determine the time of descent. We calculate the terminal velocity by dividing the length of descent with the time of descent. We have fixed the length of descent as 50 centimeters, so we are measuring only the time of descent. Time of descent is the time interval between the time of entry at the first marker and the time of exit at the second. It's difficult to do this with the regular videography, which is generally shot at 24 frames per second. So we are shooting this video using the slow motion feature. It is recorded at 240 frames per second and projected at 30 frames per second. What this means is that events that occur over a period duration of 1 second in real time get stretched out to 8 seconds of playing time. This allows for a precise measurement of the time of entry and the time of exit to within 1/100th of a second, greatly reducing the synchronization error. I will now play the slow motion video for all the three trials. Pause the video precisely at the instances of entry and exit and record the in time and out time. If required, rewind the video and replay it. This is the first trial. Pause the video and record the time of entry. Resume the video. Pause the video, record the time of exit. This is trial number 2. Pause the video and record the time of entry. Resume the video. Pause the video and record the time of exit. This is trial number 3. Pause the video and record the time of entry. Resume the video. Pause the video and record the time of exit. Finally, we are done with the data collection. We have collected the in time and out time for all the 3 trials. From the time of entry and time of exit data, calculate the time of descent for all the 3 trials and take the mean value. That is the mean value for the time of descent. We are now done with the data collection. Assemble all the data under the observation table shown here. Record all the quantities in the CGS system so that when you calculate the coefficient of viscosity, you automatically get its value in poise, okay, which is the CGS unit for the coefficient of viscosity. Usually viscosity is expressed either as Pascal second or as centipoise. Once all the data are assembled, use the expression for the coefficient of viscosity and calculate the viscosity. And in this case, like the viscosity comes to a value of 11 poise. In centipoise, if you want to write, it will be 1100 centipoise. It looks like it's either the castor oil or the glycerin. Okay, so these are the 2 liquids which have viscosity value coming close to 1000 centipoise. We set out to find the coefficient of viscosity of the liquid. We have found that. So now express the result. The coefficient of viscosity of the liquid written to correct significant figures is 11 poise or 1100 centipoise. In performing this experiment, we have to exercise the following precautions. The liquid should be transparent enough for the ball to be clearly visible. The stop clock must be read exactly at the times of entry and exit to minimize synchronization error. The balls used must be perfectly spherical and must be of the same dimension. Here are some possible sources of error. The liquid may not be of uniform density. synchronization error in reading the time of descent. The balls may not be perfectly spherical and there may be slight variation in their dimensions. This brings us to the end of this activity. I hope you enjoyed it. Thank you so much.